Good morning, class. Here's chapter 5, integrals, sections 5.1 to 5.3, the fundamental theorem of calculus, FTC. So we're going to cover the fundamental theorem of calculus, and then the next section is the substitution. Reminding you of basic integration formulas. If the derivative of kx is k and k is a number, then the reverse process going this way, the integral of k dx must be kx plus c. That's how we looked at the anti-differentiation, also known as integration. If the derivative of x to the power of it is n x to the power of n minus 1, the integral of that must be 1 over n plus 1 x to the power of n plus 1 and a constant. And we looked at it two ways. One, we looked at the steps involving differentiation. There were two of them, multiply by n, subtract 1 from it. And for integration, we went with the reverse process. Instead of subtraction, we're going to add 1. Instead of multiplication, we're going to divide. And believe it or not, that's a proof. Also, we looked at the derivative of the right-hand side, and we ended up with x to the power of n. Differentiation from the right results in the differentiation on the left results on the right. So if you integrate the right, you must get the left. In other words, if the derivative of e to the power of x is x, the integral of e to the power of x dx must be e to the power of x plus a constant. The derivative of natural log is 1 over x. The integral of 1 over x must be natural log and a constant. The derivative of sine is cosine. The integral of cosine x dx must be sine x plus c. Now this one. If you want to stick with it just the way it is, the derivative of cosine is negative sine. So the integral of negative sine x dx is positive cosine x, but we don't want to use negative. So we multiply both sides by negative. This becomes minus, this becomes positive. So the integral of sine x dx must be cosine x plus a constant. The rest of them follow in the same manner. If the derivative of tangent is secant squared, the integral of secant squared dx must be tan x. The rest of them follow in the same manner, everybody. What about these two? Just as we did with differentiation, the same happens here. If we multiply by constant, if we multiply a function by a constant and want to differentiate or integrate, that constant remains. If we have a polynomial and we want to differentiate or integrate, we do them term by term. That's the meaning of this. If the derivative of e to the power of kx is itself times k, then the integral of e to the power of kx dx must be itself divided by k. And that's the answer. So this is how we went over this process. Now, 5.1 to 5.3, the fundamental theorem of calculus, we're going to start with the method of exhaustion. Areas of familiar polygons, such as triangles and rectangles, enable us to find the area of more complicated region by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. For example, when they didn't know the area of a circle was pi r squared, then they inscribed it with 3-sided a triangle, then 4-sided a square, and so on and so forth. As you can clearly see, when we add to the number of sides, the area becomes closer to the actual area. In this case, almost it's identical to the area of it. So the area problem is the same thing. You want to find the area under the curve S, y, under the function y equals f of x, you call it S. This area, it is not a known geometric shape. We don't know the area. So to find the area of a region S that lies under the curve y equals f of x from A to B. So here's the function. Here's from A to B. This means that S is bounded by the graph of a continuous function f, where f of x is greater than or equal to 0. The vertical lines x equals a, x equals b, and the x-axis or y equals 0. So to explain this mathematically, we can write S is a set of points x, comma, y, such that x is between a and b, y is between 0, and f of x. This is mathematically explained. Now, how do you find the area? Well, you can approximate it in the following manner by using what's called the Riemann sum. Okay. And the Riemann sum says this summation of I going from 1 to n, f of x of I times delta x, which is f of x of 1 times delta x, all the way plus all the way to f of x of n times delta x. Delta x is b minus a over n. So what we do, we cut the interval of a to b into n subintervals. And we can find any width we want, but we want to make it easy, so we find width to be identical. Delta x is b minus a over n. In this case, we have cut it into 4 equal parts. So b minus a, this distance, delta x, I'm going to put it up here, is b minus a divided by n. The choice of n for us is 4 here. Now, what is the height? Well, you can use the left endpoints, the right endpoints, the midpoints, or anywhere in between. So if I use the left endpoints, that means this one, for example, the very first one, the height is this much, f of a. The second one, the height is this much. The third one is this one. And the fourth one is this one. And you can calculate those rectangular strips, their area of each piece, and add them up. Becomes an approximation. Or if I use the right endpoints, this one, this one, this one, this one, I get a different size rectangle. And the sum will be different, but that's an approximation. So the approximation is somewhere in between. I may even use somewhere in between, like the midpoint. This is right in the middle. So this is the height. So you can use any point here. The left one is the height, that f of a. The right one, f of a plus delta x, or the midpoint, or anywhere else. Makes no difference. It is an approximation. That's a methodology. We are going to do this as an example, reminding you of the Riemann sum. The function f of x is a positive function on the interval of a to b, determine the area. In this case, determine the area between f of x equals x squared plus 1 and the x-axis from 0 to 2. In other words, we want to determine the area of the shaded region. Remember, y equals x squared is a parabola that opens up from here. Y equals x squared plus 1 is the same parabola shifted up by 1 unit. In other words, this should be the graph, but we just want this portion. So we are going to go with this shaded region just to make it easy to understand. So I'm going to erase my work. And so let's say we are going to cut this into 4 rectangles. By the way, you have that in your notes. You can just pay attention to the concept. So how do we calculate the width when n is 4? Delta x is b minus a over n, so it's 2 minus 0 over 4, or 1/2, or 0.5. So 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2. We can see that delta x, the width is fixed, but what is the height? Well, you can choose the height to be the right endpoints, the left endpoints, the midpoints. For example, R4, R stands for the right, 4 stands for the number n. So let's go with the right endpoints. In which case, let me use a different color actually. This is the first one, second rectangle, third rectangle, fourth one, looking like this, which of course is larger than the actual area, but that's an approximation. So each one has a width of 0.5 or 1/2, 0.5, 1, 1.5. Because we want to go with the right endpoints, the very first one has the height f of 0.5, the second one f of 1, third one f of 1.5, and the last one f of 2. So we are going to say 1/2 the width times the height. F of 1/2, f of 1, f of 3/2, and so forth. Of course, what is f of 1/2? Plug it in here. 1/2 squared is 1/4, plus 1 is 5/4. What about 1? 1 is squared, 1 and 1 is 2. What about 3/2? 9/4 and 1, 13/4. What about 2? 2 is squared, 4 and 1 is 5. So you multiply, you add them up, you get the area of 5.75. So what is the area under the curve? Obviously, not 5.75, but it's fairly close and it's smaller than that. Let's look at the left endpoints. Let me erase my word. So the left endpoints, this is the first one, second one, third one, fourth one, looking like that. And so this time, again, we have the same width, but the height for the first one would be f of 0, the second one f of 0.5, all the way to the end. Notice the first three here and the last three are identical. So this is helping with the calculation. You don't have to repeat the calculation if you're doing it by hand. So evaluate and plug in, and you get 3.75. So what is the area? Somewhere between the two. The area is between 3.75 and 5.75. As you can see, the difference between the two is number 2. That's fairly large. But that gives you an approximation, and that's the idea behind this methodology. By the way, to make this easier, when I want to do the calculation this way, from 0 to 2, from A to B, I'm going to draw a line segment. The first one is A. A happened to be 0. The last one is B. For the right end points, everybody, I'm going to use all of these endpoints except the first one. Notice f of 0.5 or 1/2, f of 1, f of 1.5 or 3/2, f of 2 is used for R4, but f of 0 is not. So the first one is not used. That's for the right endpoints. What about the left endpoints? I'm going to use all the endpoints except the B. Take a look. F of 0, f of 1/2 or 0.5, f of 1, f of 1.5. So when I do that, it's really, to me, it speeds up the process. If I happen to want to use the midpoints, then this is my first midpoint. And then I add delta x. The second one, the third one, the fourth one. So this line segment is really a lifesaver when you have to calculate. Now we're going to repeat the question, and this time we're going to go with n equals 8, just for the sake of argument to see what happens. Having said that, when n is 8, your delta x b minus a, 2 minus 0 divided by 8 becomes smaller, 1/4 or 0.25. So we can use the right endpoints, we can use the left endpoints. If we use the right endpoints, notice, if you look at the rectangles, clearly they show you a better approximation. So the width is 0.25 or 1/4. The height For the right endpoints, all of these endpoints, remember, just the first one is not used, right? This is what you get. And we factor the 1/4 or 0.25 out. F of the very first point is 0.25 or 1/4. So F of 1/4. The next one, 2/4. On purpose, I'm keeping it as over the denominator 4. I'm not changing it, which of course means 1/2, 3/4, 4/4, or 1. And the rest of them you evaluate it and you get 5.1875. We're going to do the same thing for the left endpoints. And for the left endpoints, everybody notice we use all the endpoints except the last one. So f of 0 is being used, f of 0.25 all the way to the end. Notice L8 is 1/4 times f of 0 all the way to f of 7/4 or 1.75, not f of b. So f of b or f of 2 is not used here. F of a or f of 0 is not used for the right endpoints. Again, notice for the right endpoints, we use f of 2, which is not part of the calculation for this one. For the left point, f of 0 is not part of that. The rest of them are identical. And the purpose of that is to tell you, okay, save time. So put it into calculator. You come up with the answer. What is the area? When n is 8, somewhere between 4.1875 and 5.1875. By the way, we have done it with 4 decimals. You may want to do it with more. But in any event, let's compare it to what we did with n equals 4. In the case of n equals 4, the difference was 2. Now the difference is 1. Clearly, it's a better approximation. So approximation gets better as n gets larger as we expect. Now, what type of a function is this? This is an increasing function and it's CU, concave up. Generally speaking, if the function is increasing and concave up, right endpoints will overestimate the area, left endpoints will underestimate the area. So increasing and concave up will do that. So here's the fundamental theorem of calculus again. Suppose a continuous function f is defined on the interval of a to b if the interval is divided into n subintervals so that delta x is b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x sub 2 is a plus 2 delta x, all the way to the last one. X sub n is a plus n delta x equals b. Then a Riemann sum associated with f is the sum, which indicates the summation of I going from 1 to n of f of x sub I delta x equals f of x sub 1 delta x plus all the way to the end f of x sub n delta x. What is x sub I? X sub I is any point in the subinterval of a sub I minus 1 and it's a sub I. So any point in between, as I mentioned, the left hand point, the right, or the midpoint. Now, what is the geometry and procedure, which is called Riemann summation? Partition the interval of a to b into a few. How many? Maybe 4, just as an example, subintervals. Therefore, if you go with 4, you make 4 rectangles. The width is delta x equals b minus a over 4. The height is f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4. Again, any of them, end points, left, right, midpoints. Then add more, make it, for example, 8 or more. As the number of rectangles increase, the approximation gets better. So for the left endpoints, right endpoints, and midpoints, we have the formulas. For example, ln, rn, or mn, they start with delta x. And we put brackets, we add up f of x sub 0 plus f of x sub n all the way up to f of x sub n minus 1 for the left endpoints. Right endpoints, we start with f of x sub 1, and we end up with f of x sub n. The midpoint would be x sub 1 bar. That means the midpoint between these two. Do I have to memorize that? No, when I do that, I would put A here, B here. Then I would cut it into, I don't know, so many pieces as I'm asked. And if I'm using the right endpoints for, let's start with the left endpoints. With the left endpoints, I'm not going to use B. And I'm going to use the rest of them. For the right endpoints, I'm not going to use A, but I'm going to use the rest of it. For the midpoints, I'm going to find the first midpoint here, and then I'm going to add delta x. And I evaluate the function at those points. Or just follow the formula. It makes no difference. So the Riemann sum, A equals summation of f of x by delta x as I goes from 1 to 4 is this, and it's an approximation. And the area under the curve is exactly the limit of the summation I going from 1 to n of f of x by delta x as n goes to infinity. Delta x is b minus a over n. X of I is a plus I delta x. Now, we can use that, and it's pretty tedious. There are two fundamental theorems of calculus. Some texts, they say this is the first one, this is the second one. Some say it's otherwise. It makes no difference whatsoever. This one says if you integrate f of t dt from a to x and differentiate it, they will undo each other and they give you the function at the upper limit x f of x. The other one says if you want to evaluate the integral of a to b f of x dx, evaluate the antiderivative at the endpoints f of b minus f of a, where capital F prime is lowercase f of x. This is identical to this one and represents the area under the curve if it's positive. It represents the difference of areas if it's not. So the definite integral. What is the integral of a to b f of x dx? Let's look at each piece. Integration symbol. That is an elongated S. The symbol was introduced by Leibniz and it's called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. A is the lower limit of integration. B is the upper limit of integration. F of x is what we are integrating, anti-differentiating integrand. Dx is the variable of integration. Okay. And the reason it's called the dummy variable, it is called the dummy variable because the answer for this is a number and it doesn't matter. Does not depend on the variable chosen. The dx simply indicates that the independent variable is x. So the integral of a to b f of x dx is a number. It doesn't depend on x. We could use any letter in place of x without changing the value of the integral of a to b f of t dt. Or its approximation, the integral of a to b f of x dx, is the summation I going from 1 to n of f of x of I delta x, which is f of x of 1 times delta x, plus all the way to the end f of x of n delta x. This sum is called the Riemann sum. And the precise value, which gives you the area under the curve if the function is positive, area is the limit as n goes to infinity of summation I going from 1 to n of f of x of I delta x. And now, what's important to understand, the area is this limit, but it's easier to use the fundamental theorem of calculus. So we're going to look at a couple of examples and use both of them. For example, evaluating the integral using areas, the integral of minus 2 to 5, 3 times dx. Note, the integral of a to b f of x dx represents the area under the curve f of x from a to b if the function is positive. Otherwise, it represents the difference of areas, the signed area interpretation, of the definite integral. That's important to understand. So let's go with the concept of areas. And what function are we dealing with? Y or f of x equals 3, which is a horizontal line. So we're going to draw a horizontal line, and we are interested from -2 to 5, so plotted over -2 to 5. So here's the grid. Here's y equals 3, a horizontal line. And from -2 to 5, of course, the y coordinate is fixed at 3, so -2 comma 3, 5 comma 3, and we want the area of this rectangle. So to find the area of a rectangle is the width, or you can say the length, times the height, and the height is fixed at y equals 3. So this height is 3. What is the width? From -2 to +5 is 5 minus -2. In other words, this definite integral represents the area of a rectangle of width 5 minus -2 or 7, height 3. So this integral is the product of 7 and 3, or 21. Now, according to fundamental theorem of calculus, the integral of a to b f of x dx is capital F of b minus f of a. So let's evaluate that. So 3, when we integrate, we get 3x plus c. We don't need a constant. And the reason we don't need a constant, because we are supposed to evaluate it at the upper limit, that means plug in 5. Then we have to evaluate it at the lower limit and subtract that from the upper limit. So the c will cancel out. So we can factor the 3 out. We plug in 5 minus -2, and obviously we get the same answer. So what is that telling us? If we are interested in finding this, using the area method works, using the fundamental theorem of calculus works. We are going over this because what happens when the area method fails because it's not a geometric shape we are familiar. Here's another example. Evaluate the integral using signed areas. Use the signed area interpretation of the definite integral to compute the integral of -2 to x dx. So what happens here is that the function y or f of x equals x, the interval of -1 to 2, and y or f of x equals x is a line through the origin. So that's the line. And from -1 is here, to 2 is here. We are looking at this area minus this area. Y minus, because we are looking at signed areas. When the function is positive, when you evaluate this integral becomes positive. When it's negative, the integral becomes negative. So the result could be positive, negative, or even 0. So it represents the signed area, difference of areas. If you want just the area, you have to go with an absolute value. So having said that, you notice each one is a triangular shape, which follows area equals 1/2 base times the height. And you also notice this point has coordinates 2, 2. This point has coordinates -1, -1, which means this distance or height is 2. This base or this distance is also 2. So the area for the green one is 1/2, 2 times 2, or 2. Now, this distance is 1, this distance is 1. So the area for the red one is 1/2 times 1 times 1. Therefore, this integral that represents the difference of areas would be the area of the green 2 minus the area of the red 1/2, and that gives us 3/2. So we can calculate this easily because the two shapes are triangular shapes, and we have a formula in geometry for that. However, as we said, the fundamental theorem of calculus will result in the same answer. And as you know, the antiderivative of x is half of x squared, and we want to evaluate it from -1 to 2. So 1/2, we keep it out. We plug in 2, we get 4. We plug in -1, we get +1. So 4 minus 1. So half of 4 minus 1 is 3/2, as expected, is the same thing. In other words, we can calculate the area using geometry. We can calculate the area using fundamental theorem of calculus. What does it show? If this fails because it's not a geometric shape we are familiar with, we can always rely on calculus and fundamental theorem of calculus. What I'd like you to do is to graph and use signed areas to show that the integral of -4 to 1/6x dx is -45. I'm giving you the answer. I want you to do it two ways, just the way we did here with the graph, as well as how we did it with the definite integral. Do them both ways, and you'll be very comfortable after doing that with this concept that was mentioned here. We want to evaluate the integral of 0 to 1x to the power of 7 dx. So the integral of a to b f of x dx is capital F of b minus f of a. So antiderivative is 1/8 x to the power of 8. You don't need a constant, and you want to evaluate it from 0 to 1. So we keep the 1/8 out. We plug in 1, we get 1. Plug in 0, we get 0. So 1/8 times 1 minus 0, and it's 1/8. It makes no difference, even if we put a c here, because we have to evaluate it at 1 and 0, the c cancel out. Tip, even if we use another antiderivative, capital F of x plus c. In other words, if I put a plus c here, in the evaluation theorem, the result will be the same, because capital F of b plus c minus capital F of a plus c, the c's cancel out, is capital F of b minus f of a. So you might as well ignore the c, because the result is number. You cannot ignore the c otherwise, as is the case here. Okay, so what about the integral of 1 to 2x to the power of -1 dx? 1/x or x to the power of -1 are the same. The answer is the natural law. We don't need a constant because this is a number. So we plug in the upper limit, we plug in the lower limit, so ln2 minus ln1. I don't need an absolute value because both limits 1 and 2 are positive. So this is obviously ln1, 0. The exact answer is ln2, everybody. And keep it exact. What happens here, I'm going to have exactly the same answer with different limits. So that's why it's ln of absolute value of x from -2 to -1. The difference between the two is, in part B, I didn't need the absolute value. In part C, I must use the absolute value because the limits are negative. And natural log of any negative number is undefined because the domain is from 0 to infinity. 0 is not included. So we have ln1, which is 0, minus ln2, and that's the exact answer. And we're done. The integral of 0 to pi sine x dx, as you know, the derivative of sine is cosine, but the integral is negative cosine. So minus cosine x from 0 to pi. To evaluate this, I'm going to take the negative sign out and write down minus cosine pi minus cosine 0. Cosine pi, as you know, it's -1, minus cosine 0 is +1. This is -2, negative outside makes it +2. Very straightforward, everybody.